Hello everyone, my name is Parusha and this is my Lab8 demonstration for clustering and feature analysis using the UNSW-N15 cybersecurity dataset. So let's start with the task 1 where it says K means clustering. So I'm gonna quickly open Lab8. So yeah, this is my Python file for the task 1 where like it actually first I install the dataset and load into the Python, and it includes the 49 network traffic features such as packet count, payload sizes, TCP flag, timestamp, and more. Then basically the script here is doing loads the dataset, convert the categorizable field like proto service state into numeric codes. Then it applied standard scaler to normalize the feature. And then basically after scaling, the script will run for k means clustering with the three values k equal to 2, k equal to 5, and k equal to 10. And then I use PCA to reduce the data into two components for visualization. And finally, it's gonna identify the top 5. As you can see, where it's gonna identify the top 5 features for that. So I'm gonna first run Python 3 lab8.py. It's running. It's gonna take some time. Yeah, yeah, it's done. Here you can see there are no errors in the task one and it runs properly. So basically, let's see over here. So this is the actually the first graph which I got from the I got from the here thing. So what's exactly the graph here doing? So the graph here doing is actually it plots the k clustering for the data set k equal to 2, and it has major two groups which represent the broad difference in network overflow. One cluster mostly represents the normal traffic, where other cluster is showing the indicates about the abnormal traffic, but the PCA transformation helps over with the 2D plane. So this is a k2, then this is a K5 data set splits into smaller and more detailed subgroup, as you can see over here, and the cluster represents the different types of network activity. The separation becomes the clearer for some cluster while the other overlaps significantly, indicating mixed traffic behavior. And for K equal to 10, it's very like means very small cluster capturing fine grained patterns. They provide a deeper insight into traffic variation but increases overlap because dividing too many clusters reduce accuracy. So it shows how like higher k values increase detail but it reduces the cluster purity over here. Then for the next, I'm gonna show you these are my top features which I got from the CSV for k equal to 2. So for k equal to 2, the top 5 features are ISMN IP port, which scores around 10, then SIN SYN TP packets, then Proto, then SRCIP, and the CT state TTL. These are the top 5 features for K2, respectively, same like the other, like S byte, sloss, S bytes are the top features for K equal to 5, and these are the top 5 important features for K equal to 10 over here. As I can show you here, I do have a CSV file over here. Ls cd out cd lab a, and then a, cd lab 8a, and cat, yeah, top feature.csv. Oh, top feature.csv. Yeah, as you can see over here, it's giving the same output as in the graph. So yeah, that's for my task 1 here. So now let's move to the task 2. So for task 2, I'm gonna first clear here everything, and then let's move to the task 2. Cat cat lab 8 b dot 5, as you can see over here. So basically this is my task 2 script over here, from starts from here. So yes, so what's the exactly task 2 script doing? It loads and encodes the data set first. As you can see over here, first it's gonna load and encode, and then it keeps only the numeric column. So uses Pearson correlation to compute a correlation matrix, and it also generates a heat map to visualize the relationship and extract the top 10 correlated feature pairs, compares and then compares this pair with the k means clustering feature. So yeah, so let's start running this. Python 3 lab 8b.py. It's gonna take some time. Yeah, as you can see over here, it like these are the top 10 features for k2, top here for k, like for task 2. Sorry, these are for the task 1, and these are the top features for the task 2. And as you can see over here, there are no common significant features found in both task 1 and task 2. So yeah, so for task 2, let's start with the first heat map we got. Okay, so basically I need to go back to this. Yeah, this is the output, this is the heat map which I got. Yeah, this is the heat map. Visualize the Pearson correlation values between numeric feature. Here the red indicates the strong positive correlation, while the blue ones here area shows the negative correlation. So features such as LT time, as you can see over here, LT time and S time are strongly correlated, meaning they increase together and carry the more information. So this is from the heat map, and then again we need to go into cd out, cd lab 8b, and then ls. So yes, for the first we're gonna go to correlation underscore matrix. Yeah, so this is the file. As you can see over here, it has like a c, this is the file. CSV contains the Pearson correlation values for each features and pair. It allows analysts to identify the redundant or highly related variables that may impact the cluster. So this is the metric file. Then we're gonna go to the cat top. Yeah, so these are the featured 1 2 correlation. These are the top features which we got from the second task here correlated, and these pairs are important for understanding which attributes move together and may influence network jointly. And then for cat common, yeah, so here as you can see over here in the common one, since the clustering and the correlation measures different type of relationship, so no feature appears in the both lists. So this is normal and expected from the dataset, as we have nothing in the common dataset. So now let's gonna move to task 3 quickly. R. So for task 3, I'm gonna start lab8c.py. Oh, oh yeah. So basically this is the script for my task 3. So actually the script loads here the dataset and all the columns names, select the subset and important feature like s byte here. This is the all, and then it's gonna select over here s byte, sk, pt, swin, dwin, l time and s time, and then it's gonna sample like from the 1000 rows to avoid the memory overflow. Then it's gonna run hsc like HSE with K2, K5 and K10. As you can see over here, it's gonna run, and it's gonna run this and it's gonna generate some plots. So let's move on that. So let's gonna run Python. So as you can see, I just started running the task 3 script, and as you can see over here, the task 3 script has been run perfectly completed, and it created all the plots and graph. So now let's look at the graph. So let's start with the k equal to 2. So yeah, so what this graph here is doing, so here the HSE clustering k equal to 2 graph forms like two major groups similar to k-means. Cluster boundaries are shaped by the hierarchical merging rather than centroid distance, resulting into more grouping, as you can see here in the K2. So now in K equal to 5. So with the K equal to 5, it creates a medium size cluster over here. And this represents a different like flow behavior such as varying session duration, or like traffic, maybe traffic intensity. And HSE also produce a less circular shapes compared to the K clustering means. Now let's move to the K10. So as you can see over here in the K equal to 10, so here it gives a more detailed structure. Some clusters are even overlapping each other, and the clustering does not optimize the distance in the same way K means do, but it still gives some structure compared to the low K values. So these are the K values. Now let's move on the scalar like scatter plot for L time versus S time. So the here the what they are doing are they are almostly linearly related, and their tight diagonal pattern confirm that they have a strong correlation detected in the task 2, as you can see over here. Then let's move to the S byte versus S packets. So what here is they are doing is actually they have a upward pattern, shows that higher sent bytes usually correspond to the higher number of packets sent, confirming they have a logical traffic flow relationship over here. And then for the S-win versus T-win graph, they have a clustered point multiple traffic patterns, where you can see over here multiple pattern where the source and the destination window sizes are differ, and this helps HSE to identify the structural pattern in TCP overflow. And the final graph, which is the dendrogram using the word linkage. So what exactly the dendrogram here doing? So dendrogram shows the clusters merge at a different distance. As you can see over here, the clusters are merging at different distance, cutting the tree at a different height corresponding to the different number of clusters. And also the middle section, this means this one, the middle section shows suggest around 4 to 6 natural clusters matching K clustering means over here, as you can see over here. Yeah, so this is what I got from the dendrogram. So now let's move on to the task 4. So the task 4 actually is like comparing K means and the HSE method, which one is the best. So as I hear the both pattern applied in the data set, and the K cluster like K means clustering has the data set into well separated circular cluster by minimizing the distance between each data point assigned a cluster centroid. However, the k-means clustering assumes a spherical cluster and may struggle if the data has an irregular shape overlapping the point. Whereas for HSC clustering, they have followed by the bottom-up approach, starting with the each data point as an individual cluster and merging them step by step based on their similarity. So the dendrogram visualized clearly displays how the clusters merge at different linkage distance, giving a deeper insight into the structure and relationship between the points. However, the HSE was more memory intensive and slower compared to the K-means, which required a sampling of data for success execution. So, finding for the summary, the K-means provide a faster and more efficient grouping for the large dataset, while HSE gave a detailed hierarchical structure but computationally heavy. Both algorithms identified the similar clustering pattern, validating the dataset internal structure. So for the conclusion here, I will say through this lab, I have learned how supervised learning can detect anomalies, categorize traffic, and improve IDS. Overall, this was an this lab provides a pre-processing, feature selection, and applying the clustering algorithm to the real-world security dataset. Thank you.